Hey everyone, I'm gonna try something here as I've been a bit unproductive on a Friday afternoon, so I just want to try something a little bit different. And what I'm gonna do is maybe not live code, but I'm gonna, in real time code up a machine learning model to do some weather prediction stuff. So let's just jump right into this here. We're going to be using data from dynamical.org. They're just the ones hosting it. It's going to be GFS data from NOAA. And as you can see, I'm on dynamical.org. I can go to their catalog, and we're going to use their analysis data. So not the forecast data, but sort of the historic run. So this is 0.25 degrees globally, and it is, they got about 10 years at an hourly time step. And then the variables that they have here are wind speeds and the temperature, near surface temperature and surface precipitation. So the nice thing about this data is you can just grab the link to the ZAR file, and we'll be able to use that to pull data directly over the network. So that will be nice and convenient for us. The other two things that I want to, well, I guess there's three, but there's two in this browser. I'm going to be using PyTorch for this, fairly standard, nothing crazy there. I recommend you learn PyTorch if you want to do deep learning. And I'm also going to use UV to manage my environment. So UV is really nice. I'm just getting started with it, to be honest, but it's quite a bit faster than Conda, and it has some other nice tools. So let's switch us over here. So I'm in a blank folder in VS Code, and we're gonna go ahead and gonna hit Control tilde there to get my terminal. As you can see, I'm in this particular folder. I like to, because I'm gonna keep this terminal open long term. I might wanna have some other windows with different files open. So this is what I'm using here. So I just pulled that little thing over into my tab. So, okay, first thing I wanted to do is UV init. Okay, and UV init creates a bunch of files for us. Nice. Most of that we can just kind of gloss over until later. The other thing I'm going to do is I'm going to do tmux.a, nope, not tmux.a, tmux. I'm just going to create a new session of tmux for me. It's not important. It just, if I lose connection to the server that I'm working on, then it will. I won't lose this terminal session. It will just live on in the background. So that's why I'm doing that. So what I'm going to do is then, so I've initialized my UV project, and then I'm going to also do UVVN. Whoops. So this just creates a virtual environment. Okay, we've got that activated. Now we can start adding our dependencies. So I already mentioned we're going to be using Torch. You may have gleaned this from the dynamical stuff, but they are serving up their files via ZAR, and I'll be using some standard stuff with ZAR like Xarray to load data. So let's get some of these dependencies installed. So let's do go ahead here, and I'm going to do UV add PyTorch, it's just torch vision, torch audio. This is, again, just to give you this is what they tell you to install here. They use pip for this, but I'm just using UV because it's more convenient right now. So we need ZAR, we need, what else do we need? IPy we need Jupyter, and you can always just like UV add stuff later if you forget something, and I'm sure I will in this. I know I want Dask, I know I want distributed. Oh, it's always a little bit hard for me when it goes over that line. Distributed, matplotlib is for sure. Bokeh for the Dask dashboard. Might as well just say NumPy and Pandas just in case. One of these I probably, yeah, distributed, I spelled wrong. There we go. So then I need to do python-m ipy kernel, and I'm going to go ahead and sorry, I always forget how to do this. ipy kernel. Okay, yeah. So as you can see, I already had one failed recording of this just because of a dumb thing, but here we go. So boom, we got that. Okay, so now I'll be able to do this. So now what I usually like to do is have a source folder and a, not inside of the source folder, but out here, and a notebooks folder. And inside the source folder, I'm just going to pre-populate one thing. Okay, we don't actually need to put anything in init.py right now, but that is just so that we can import stuff later from the source directory. So sorry about that. In here, we're going to do data exploration.ipynb. Okay, so we've got ourselves a nice little notebook. Let's get that up in here. Let's go ahead and, so we're using the m2m tutorial kernel. So that's got all the packages we just installed. And we'll go over here, get XR. So we need import xarray as xr import matplotlib. Yeah. So you'll see some of those auto completions. I have GitHub Copilot activated. I will try not to rely on it too much to write code, but it is useful for some things right now. So I'll go ahead and just pop those open. ds equals, oh, I probably need to, did that. Maybe I need to restart the kernel. Did I just forget xarray? Yep. Okay, forgot xarray. Restart, clear that out. Try again. All right, let's open this data set. Oh no, I forgot. I definitely knew I needed this. So uv add. Okay, restart that, clear it all up. Get it going again. And I think this time we should be fine. Okay, so here we go. We can see what's in the data, and let's also do it really quickly. Let's work with temperature. We'll just make that the variable of interest. We can do that. So as you can see, this is a relatively large data set. I think each of the variables is 350 gigabytes or so. But yeah, it's 721 by 1440 with a whole bunch of time steps. It's hourly, so here we go. Nice, we got a good plot. We can see the world. The values look pretty reasonable. Okay, so I think that's good. Now, let's actually talk about the problem we want to solve. So I'm just making this up as I go, kind of. But I'm going to say that the problem that I would like us to solve is going to be to maybe take the last 5 days of temperature data, or 5 hours, and predict the next one. That seems like a relatively, reasonable task to try and perform. So to do that, we only need the temperature data, and we're just going to need to be able to process some of the time stuff. So, okay. So I just want to highlight this because it's worth a second. The PyTorch documentation is really good. I highly recommend you check out some of these learn things like the PyTorch recipes. They got all sorts of great stuff in there. But I'm going to just do this kind of from the hip. I kind of know exactly how this is going to go. if there's anything that, while you're watching this, you just are like, whoa, that came out of nowhere, go ahead, pause the recording, and, go do some Googling on your own and find out what each of these things are. So, and that's just in the interest of keeping this recording, under 5 hours or whatever it's going to end up being. We'll find out. But I am going to go ahead and pause the recording for a second and then come back and we'll start developing our data set code. All right, and back. So, as I mentioned, we're going to get started on the data set code. But before we do that, I think it might be valuable to talk through exactly kind of what I already know the high-level structure of this project is going to look like. So the data is usually where I prefer to start on an ML sort of project, because it's the thing that's going to, one, take the most time, and two, probably inform a lot of the decisions that you make with models or other infrastructure. So sort of getting familiar with and really getting to know the data first is to my mind the most important piece. I'm already relatively familiar with the NOAA GFS data, and I also know that this data is relatively complete and free of, let's call them anomalies or glitches or whatever. If you're working with like field data or stuff that it needs cleaning, this process will take a lot more time. So don't be surprised or discouraged if, you try and do this for your own data set or whatever, and it looks a little bit messier. So I'm going to close all of that up. We know what's in this. I already said we're just going to work with the temperature data, and basically we're going to try and pull a few days of past history to predict the next one, or maybe even more, but let's start with one. Let's keep it simple. Okay. So how do we do this? Really, I mean, we're gonna keep it global. I think let's go for it. Let's keep it global prediction rather than pulling some little cutout or whatever, which you totally could do and would be an interesting task in itself. But we're gonna do different. So okay. Okay, so I know that we're going to want to put this in a torch data set. Sorry. Okay, so I know that. So I'm going to re-import some stuff. And, the other thing I'm going to really quickly just check torch.cuda. No? Okay, cool. I just wanted to make sure that we'd be able to use the GPU. Otherwise, it would be too hard to train this model. But and that wasn't that wouldn't be a question about whether. I was just checking if the installation of the software went the way that I wanted it to, so that we can use GPU. Okay, so then I'm going to call this a GFS data set. Yeah, we'll go with that for now. I'm going to actually delete all this so that we can walk through this. I'll start actually fresh. I'm going to try it on to use Copilot. That did look pretty like a good starting place though, but for the sake of learning. So we're going to subclass the PyTorch data set, and then, you know what, maybe I will turn off Copilot here. Okay. Okay, we know we're going to need to take a data set in, and I'm just going to refer to it as yes. And then we can add some configuration options. So maybe the number of past time steps. So I'm going to say let's say, because we might have input and target time steps be different. So I'm going to say input end time steps and target end time steps. Okay, then as always, we need to do our superclass in it. If you don't know what this is, don't worry about it. Just add it in. You don't have to think about it too much, but you do have to remember to do it. And then I'm going to start adding some class instances. Oh my gosh, I don't know what I'm typing there. I'm going to stop talking so I can just type. Okay, and I'm also adding this variables thing. I'm going to break these out onto their separate lines. I sometimes like to do this just for the sake of simplicity. And I'm going to initialize that one by default to temperature 2M. I'm actually going to do this. Okay. Now, we have our init, so we can create this thing, and then we also need a way to actually get a sample out of it. So this we do with and itself, and I believe I. Let's check the docs. Oh, I should actually go back. Oh. So we're doing an iterable style of data set where we can do this. Yeah, I'm going back. I'm probably going to get to the tutorial. There we go. Okay, so this is just a tutorial. Okay, so here we go. This one's, so this one we would need to know how to do it completely. Let me just, no, okay, so this one, okay, we can do that way. And did they, is this base data set? Find out here. It's taking me longer than it probably should. Data set, yes. Okay. But I can just do, oh, but that's iterable. Get item in mind. Okay, so I'm going to do get item, not iter. Just for completeness, put pass. Okay, so with len, we're trying to get the number of samples that we can pull out of this thing. And so if we need to pull out this many time steps per output and this many time steps per input, and we are considering like a stride of 1, so we just offset the samples by 1 each, one time step each. This means that the total time steps is actually. Okay, so the total number of time steps is that, and the number of time steps in a sample is self-dat. So that gives me the total number of time steps and the number of time steps in a sample. So then round to the nearest integer should be good enough. So it's basically just saying that for every sample we need a certain number of time steps, and you just divide that by the total time steps to get that. So, so then we can do, if we want to get a particular time step, we'll need to pull out our data. So this is where the real work comes in. So let me pause here for a second and we'll get back to it. All right, so we just finished up the length there, and now we want to figure out how we actually get something out of this. So I'm not going to do this in one go. I'm going to sort of do this piecewise. And the simplest thing that we know we want to do is return, okay, I know we want to go from I to I plus okay, and let's just start there. It never hurts to do this iteratively. Okay, so I have ds, and let's say, let's do this. So we can start to create this thing. I'm just going to call this D. You can get deep down the rabbit hole of too many DS's fast, but it's GFSD set. And we want to give it DS. The self is implied always. And then let's say, let's just do 1, 1, and leave that. Okay, so when we do that, actually, maybe I should, before I do anything else, D. Okay, so D does just instantiate this little guy here, and then we can now pull stuff from it, and that goes ahead. So now you can see I'm just pulling the zeroth thing. Let's see what happens when I pull -1. That one pulls, and you saw before it was like 2015. This one now is not loaded because it doesn't actually quite know what time it is. So let's go ahead and load that. Oh, -1, it can't do. Why not? Ah, that makes sense. -2 maybe? Yeah, so -2. We can't pull the last one because, well, it'll become a little bit more clear in a second. Okay, so then we can see this one's 2024. There we go. So it's kind of working. So obviously then, and now here's the little, I guess, tricky piece that you got to keep track of, right? We don't want to go from I, we want to go from this spot to okay, that's getting a little bit long. Let's create these as separate variables. And do we want to do that as a slice or as the indices? Let's do the indices. Let's make it very explicit. Let's call it x start equals I, easy. X end. Let's just go ahead and paste that there real quick. And now we can make this. Oops. Sorry, sometimes I get a little bit out of control with my key bindings. Okay, and now we can do y start. And because Python is not inclusive, it's as easy as that. I think, I hope. When you're doing this live, you always second guess yourself a little bit. Oof. Here we go. Okay, so here we go. Let's recreate that. And okay, so let's see. We've grabbed X and Y. There we go. This one doesn't quite work. So I think we've got our length a little bit wrong. I think we need a +1. Oh. It's because of the int. I think we need to -1 from this. There's probably a smarter way to do this. I think I'm probably wrong again. Yeah, see, so what I'm seeing here is that this has some data in it, and this does not. So the length of the data set is a bit wrong. Let's see. Okay, let's go len d. And because I know I should practice what I preach, you should never use a variable before it's instantiated. Okay, so here we go. This is got supposedly 41,459 time steps. That should be about half of this. 41,000, good. And then this is where we get ourselves into trouble, right? This 920, you know, if you look at this, 920 divided by 2, 460, but I'm doing something clearly dumb here. I think this has to be a +1. Oops. This isn't going to be perfect, but it will work. Restart everything. Is there, what is going on here? What's the time? It does go through that. Something odd is going on. We should definitely be able to grab that. Because, okay, so what I'm seeing here, if I put in I as, let's even put that in there, right? 27639, because that's going to be the last item. You can get that. Oh no, that works. Oh, you must just not be able to negatively, You just can't negative index on an iterable data set. Okay, that's learning everything, learning every day. How about, okay, so I think I did this right the first time. Well, let's first grab that. We get valid times for both our X and our Y here. That's great. We should be able to grab, okay, yeah. So we need to grab -1 because we're, you know, two consecutive timestamps. But that does in fact produce that, but it does not. I think it's actually just the, okay. Okay, wait. I'm gonna pause the recording and figure this out. Okay, I'm actually very dumb. That took me like 2 seconds when I wasn't in my recording mode or whatever. It's just the subtraction. You can think that through. See why that's the case. But here we go. Okay, so that's great. Let's talk about what's actually in here. What's going on? And let's just print x in general real quick. Okay, so, and you know, so we get the pretty version. So this produces something with a 1 time step and 721 by 1440. That's good. It's got those dimensions, and it pulled out just the temperature variable, like we kind of wanted. Okay, easy, good. So next up, let's verify that some of our functionality here is working. You already saw that it did get consecutive time steps, but what happens if we actually do this with multiple time steps? So, okay, so what we want to make sure of is that we have the right number of time steps in each our x and our y variables that come out, but also, and this is important, that the times are contiguous between the x and the y. Because, right, we want to use the past to predict the immediate future, and that's what we want to make sure that we're enforcing. So here we go, 21, and I'm looking at this hour marker right now in particular. So we've got that goes next hour, and now y should be, it should say 23. Boom, good, okay. Let's double check this a little bit further, and let's just start grabbing, like, I don't know, 999. Let's grab an earlier one, let's say. But it's still like in the middle of the data set, so I just want to make sure that we're you know, I like to play around with it, make sure that things hold up. So again, 15, 16, 17, 18, nice, and they are all January or February 25th. So everything's looking pretty good. So I think we're gonna let's soup it up one more time, just one last check. It pulls 5 and it pulls R2 there. And again, now what you should see, yep, okay, still continuity. Make sure you go to the next line, T19. So that's the 19th hour of the day. Good, good. So I think we're all good. I think this works. So this isn't exactly what we need, right? So those are still like, you know, this is still a data set. We need to get this to a torch tensor. So let me play around outside the data set so we can start to talk about how you approach this. So I want, what do I want? We're going to be using convolutional neural network, as I already said. So let's search, pull up the comp2D docs. And the thing that's notable is we want to get our inputs matched up. And it says NCHW, where I can tell you N is the number of samples, so we're in batch mode. C is the number of channels. In our case, we're going to consider the variable time steps as separate channels. If you're doing something like an LSTM, this is not going to be exactly the same. And I'm not going to really distinguish that in this video, but maybe in a separate one we can talk about something and maybe even implement something like a conv LSTM. But for now, each time step will be considered an individual channel. H and W are height and width. So those are spatial dimensions. Okay, going back. We need to get our data set to have those sorts of dimensions. And actually, I should say the data set should actually provide the unbatched input. So this is batched input and this is unbatched. If you don't know about mini batch training, you should go look that up. Otherwise, just assume for now that this we'll get ourselves into the batched mode in a little bit. But for now, we're just producing these. Okay. So x dot shape. Oh, we can't do that. Oh, because it, right. You know, check this out also. Pulling these took 0 amount of time. If I hit dot values on this, it's going to take a little bit longer because Xarray is lazy. So this will still take a bit of time, but it shouldn't be too bad because we haven't downloaded the data yet. So now what's going to happen when I call dot values is it's going to go out and actually hit the internet, go out to Dynamical and download the actual array that we need. So I'm going to do that here. So there we go. This will take a few seconds, but there we go. Okay. And now, here we go. So what are these? This thing is variables. So one thing you'll note is I did this such that we could include multiple variables. So why don't we just do it for fun? Oh, and actually, don't do it there. Do it in the appropriate place. What's the other? Sure, we'll just grab that. So I can copy and paste. Okay, now that's going to be 2 in the lead. Okay, so that's just worth noting. Okay, so we're almost there. So let's break this down a little bit further. X.to array. Oh, no, let's close that up so we don't get all those numbers. Stacks any of the variables in a data set into a data array with a new variable dimension. So that's this guy. If you're not super familiar with Xarray, I suggest you check a little bit into the docs on that. So real quick, we gotta pause. I think Dog's about to freak out. All right, so Beck and okay. Next up, so we know how to, and again, dot values will turn this into just a NumPy array, and then we need to do like that. Okay, but here's a problem. I mean, not really a problem, just a thing that we have to keep in mind. These values range quite a bit. Uh-oh, we've got a bunch of nans too. What's going on there? Actually, so what I was going to talk about is normalizing our data or standardizing it using z-score type method. But let me just really quickly see. Oh, I guess precipitation's got maybe a different time extent or whatever. We're not going to be concerned with that because we're just doing temperature. You know what? Let's, as I said, flying by the seat of our pants here. Let's just say variable. Let's just get rid of the concern about that. So now, of course, you gotta watch yourself here. It actually should be good. Okay. Okay, now we don't need to do the to array thing because we're just pulling out one variable directly. It's always going to be a data array. When there's multiple variables inside of the Xarray data set, it remains a data set. So I'm avoiding that. So now I should be able to do dot values directly, and I'll just go ahead and dot shape it. So here we go, x dot values. Boom. Okay, and you see we no longer have that first dimension. That's actually going to be a little bit simpler for us later. Okay, good. Okay, so I did that, but actually I'm gonna do one real quick thing. I want to show you a thing really quickly. Yeah, here we go. Okay, cool, 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 cool. So, what we want to do is normalize this data. So there's two ways that are kind of common to do this. You can either standardize it, which is like z-score, where you subtract off the mean and divide by the standard deviation, or there's regular ass normalization, where you just divide by the range, essentially. So because I was just looking at this, so I guess we only have the mean, so we can't really standardize this. So we'll have to use the min and max actually. So we're gonna scale it between these values. So this is basically we want the max value to go to 1 and the min value to go to -79. Okay, so let's see. To do this, like running that calculation is not hard, but I'm just thinking future wise, because we're going to want to be able to untransform this data later, right? That way we can, when we run the model, we can make our rescaling back into physical space. So what I'm going to do is actually record those in here. Okay, so that's in adders, attributes here. You can get them by adders, and it says statistics approximate. And I'm just gonna go ahead and try this. And note, it returns a dictionary in there. So that's a dictionary, and we want max, I think I said, yeah. Okay, on that, create that, d.var min. Is that what we see? Yep, okay, and let's also double check var max. Okay, cool, so we have recorded those, and that will be useful later. I'm going to then, I'm going to pause for a second, and then I'll be right back. Okay. Let's go ahead and write a new function that we're going to call normalize. And I'm actually going to make it take a sample in. I think that makes more sense. We could just do it to the entire data set and it would still be lazy. So actually, let's do that. Okay, so what you want to do here, right? We want, where do we go? We want the maximum value to be transformed to this. So we want to divide by the range, right? And if we divide by the range, what happens? Self.es equals self.es. If you just divide by the range and you think about what's going on, what's going to happen is our minimum value is still not going to be 0 necessarily, or -1. So we actually need to subtract that off as well. So let's go ahead and write that. Okay, I'm going to actually do something a little bit different than I was originally going to. So again, we're here, we've got the data out, and we are getting to the point where we can get actual values out of this. But we still need to rescale it. And we have the max, min, and mean. Normally what you do is do something like standardization or pure normalization. So for standardization, you subtract the mean and divide by standard deviation. For normalization, you subtract the mean and then divide by the range. But it's less common to do this, but it's still going to be totally fine. I'm going to subtract the mean and then divide by the range. So to do that, let's get some of this recorded. So self dot mean equals here we go. We got to get back to here. So it's in attributes, which is attrs in code, and it's from statistics approximate. And that's going to be mean. Whoops, we only did min. And this will be max. Sorry about my cat, if you can hear her screaming. She probably wants some food. We'll get there in a second. First. And I hope those just come out as floats. So we should be able to minus self dot mean divide by. I keep doing that. Now we should be pretty much done, honestly. Let's go ahead and run that. And we get torch tensors. Let's just shape. Cool, that's good. Okay, so we've got ourselves on the up and up here. I'm going to go feed the cat, and we can get this into its own module and then start talking about well, I think we're going to talk about data loaders for a second. Then we'll get it all into a module, and we're more than halfway there. Not bad. Okay, so next up, let's talk about data loaders. Right now, this thing, as we mentioned, produces stuff with, on both x and y, 3 dimensions, and we want it to produce stuff with 4 dimensions, where this n corresponds to the number of samples in a batch. You can train these things unbatched, but they tend to perform and train worse. So let's batch it up. You can actually do this quite easily by using the PyTorch data loader. Let's just do 4 for now. And workers. Well, let's just start here first. Okay. And now, instead of getting stuff out of D, we need to get it out of DL. And let's see, I don't actually remember if it lets you directly reference, because the data loader might not know. Yeah, that's what I thought. Next. Okay, so this is a little hack thing. I'll explain it while it loads. So iter is like the function that Python runs when you put something into a for loop. So this is like it's like getting initialized for a for loop. And basically how it does that is just sort of like a dummy thing, and then next is the function that it calls every time it reaches the end of a for loop. So calling iter or next of iter of your thing is really like saying run one pass of a for loop. It's just easier for me to write that like in my head than it is to write a whole for loop and then break it after one thing. So I don't know. It's up to you how you write this. I'll just write it out for explicit. You could also write. Like it's the same as writing that, but I find that a little bit awkward to write. So I just like next of iter. And you'll see we got a nice little thingy here where we've got 4 dimensions. batch size is the first one, which is n in those PyTorch docs. So we're good to go. Not bad. Painful thing though, 20 seconds. That's not good. So that's where you can start to optimize this a little bit. And I can never remember if there's a num workers. Yeah, okay. See, this is the thing. That's a nice error message though. That's cool. Okay. So now when we do this, hopefully it won't be. That's not great. Oh, it's probably, I can't do that. No, it's going to give me the same error, isn't it? Huh. Actually, not sure what's going on there. Is it because it's an iterable data set? Let me pause and do a little bit of research. Okay, a little bit of research later. I think this is not a code issue. I think it's just the way that the dynamical data actually is served up is not receptive to having a bunch of workers. So instead of trying to use num workers here. So essentially what I was trying to do was I was originally going to make it so that, you know, we have multiple CPUs. Each of them would work on pulling together some of the samples for that batch. But instead, let's go ahead and do something a little bit different. And instead, how do I explain this? So we're going to use Dask distributed. Okay, so this is essentially going to give us a way to load data from this guy, this data set, with multiple cores. This is slightly different than doing it with the data loader because there's only one like reference or one sort of connection to the dynamical underlying data out on the web. If you use more workers here, it kind of creates extra copies of the connection here that each independently would work on it. But now it's always going to go through sort of like the same web pipe, you could say. So yeah, I think that's a decent explanation. It's not perfect, but it works okay. So the way that I was originally going to do it is usually how you set this up, where you set up individual multiple connections to the same data set. But instead what I'm going to do is create rather than many different little like pipes going to the data set, I'm creating one big pipe that gets split off at the end. So we'll do that. This does make it a little bit more complicated, but not too much more. It just means that we're going to have to create these guys up, or not those guys, the client and the local cluster up front. So client, I'm gonna turn on Copilot for this. This is one I can never quite remember the exact details of how we do it. Yep. Okay. There we go. We don't need the rest of that. And I do want to print this out. Yeah, we gotta clear everything, restart. Okay. Let that print out. I'm gonna go ahead and open this up. So right now I just set 4 workers. So that's 4 CPUs. So we'll open that data set. We'll grab this, and then we'll grab one out. This actually might not be much faster. Oh, and in fact, it might not be any amount faster. Yeah, it appears it's not even using it yet. Probably need a chunks auto. Find out. So that should probably be done. Yeah, okay. Clear everything out again. This, just to verify that, yeah, okay. So that never actually provided any updates. You would normally see some stuff on that page that I keep going back to. So let's go here, 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 here. And then finally pull some data. Let's see if this actually goes through. I'm gonna have to refresh this. Oh, never actually ran the thing. Ah, there we go. Okay, so beautiful. So now you saw, now it's grabbing our 4 pieces, but it's using multiple workers. Oh, I'm actually, that's about the same amount of time. Oh, is it because I think it might need to do some upstart. So actually, this we may need to performance debug this later. I think it's worth getting it into the modules. So okay, so how do we want to do this? We want to create ourselves a new file in here. It's going to be data.py. I'll put that over here. Okay, what do we know we want? I know we want our imports, and I know I want our class. Not sure if we need anything else. You could. You're about to see my cat get in the mix here. I think let's start there. That's good enough. Okay. So I'm actually gonna, I think we're close enough on this. I'm gonna close that up, or I'm gonna leave it open, but I'm gonna now do okay. Next up, I want to start playing with our model creation. Perfect. Okay, we'll use the same kernel, and we're going to class. Well, let's talk about ResNet. I'm actually gonna nope. Conv next. Sorry. This is a paper I really like, and a lot of people have probably seen me sell its praises, but we're going to be implementing a ResNet, which originally came out 2015, but it was used more for image classification. The sort of general architecture of the ResNet is actually quite a bit more flexible than I think a lot of people would have you consider. People will often refer to, let's see, I don't even know if there's a specific reference in here, but they'll refer to specific implementations of the ResNet idea. But we're going to take some influence from this, and then I also do want to show just the, let's see, we can just go to images. So the idea behind a ResNet, here we go. This is usually the type of thing that you do. And that's fine. It's close enough. You usually have something where you have an input, usually 2 convolutions, and then some sort of type of nonlinearity. Here in this particular diagram, they're showing batch norm as it's not an activation function, but it actually does introduce a nonlinearity. I'm going to remove this little, look at this, she's getting in the way all the time. Yeah. Anyway, it does introduce a nonlinearity, and so it could be, it's often used that way. And then you add the input back in, and you pass it through another nonlinearity. All that to say, you can see this in some of these other ones. There's two convs, and add back in, two convs, add back in. Every single time, it's the same. Why? Go read the paper. So we're going to implement that. Oh, not conf. And it wants to just straight up give us this. I'm going to say, don't do that. Okay, as always, self. We do need the in channels and out channels. I'm pretty sure that's right. We're going to want some other stuff, so I'm just going to pre-indent there. I don't really like to have the whole thing. Okay, so then, yeah, we can call that. So what we're going to do is, I'll accept that for a second. Some bookkeeping there. And then again, we want activation. And honestly, we'll go with Rayleigh. No, we'll go Gaussian error linear unit. I just like it a little bit more. It's a little bit, it gives you a little freebie. In terms of performance, it's not too much, but it is a little bit nicer. So yeah, here you go. And this is what the function looks like. So it's sort of like a ReLU, but it has this little dip down, and then it's smooth. Just the smoothness kind of is nice. I don't think we actually need that either. Okay, so this is basically the definition, the init is the definition. We're doing, and I actually probably, okay, so this is where we're going to have to busting this out. I actually don't think this is going to end up being correct. But let's go for it for the second. But of course that's going to work. And then forward. Yep, that's all that's going to need. Except it's not. Oh, no, for double conv, that's fine. Oh, gonna have to pause. So anyway, for double conv, we can just output the input, run through the sequential model here. Let me just torch dot, let's go, x equals torch dot random. Yeah, that's fine. It's batch size of 1, 3 features, and then 224. I don't know why I came up with that, but let's go ahead and, yep, create that, and bingo. Yes. Random. I'll get there. Is it just rand? Rand? Wait a second. This is a module. Must just be random. Okay. Delete. There we go. Nope. What? Torch.random. Get out. Oh, just torched out Rand. There we go. Okay. Yeah, we leave that off for now. Okay, so there's that. This thing works. The padding, essentially, I thought we were going to have to specify the padding mode as well, but I think there must be a default. The padding is, so when we've got our 3x3 kernels, it's essentially, like a 3x3 matrix, and it makes a prediction at just the center cell. So a padding of 1 avoids the edge effect. I thought we would need to tell it how to pad the data. By default, it must either just continue it or something. So there's a few different options. Like you can have it reflect so that like if you're here, it just kind of goes like that with at the edges or whatever. I don't know. That's probably a terrible explanation. But anyway, this works. So we've got a double conv. We can pass data through it. That's great. So next step, no. Class resnet module. Okay, so we're for sure going to need self. Then we're going to need to know a few things. We need to know the number of input and output channels for sure. That's the number of features or variables that you want to predict. In our case, it's like the number of input and output time steps. It's going to be the identical to these. We're also going to want to know the hidden dimension. And let's see. There's a bunch of different ways you could set this up, but I'm going to probably do this in a fairly simple way. We're just going to use the same hidden dimension, which is the internal dimension of the model across all of the double convs. And I think that's about it. Let's keep it as simple as possible. So we'll need in channels, out channels, and hidden dim. And we'll also let's pass these straight through activation equals. That way we can change them easily. Okay. As always, I'm going to copilot it so I can just tab through some of these completions. Oh, and we'll also need depth. Yep. Okay, so you always need at least this. So this is going to be our first one. Okay, and then I know that we're going to, well, we can add that, sure. That's good, and I'm going to say depth -1. That's fine. I'm going to consolidate this a little bit. That's very ugly code, I'm sorry. Whatever, it's fine. So for every layer or depth in this, I'm going to add another double conv block. And then we need self.outConv. And that's going to go from hidden dim to the out channels And okay, I'm actually going to delete that, and I'm going to put kernel size of 1. I just want this to be a pointwise convolution, so that at every pixel in the output image, we're just doing a strict pointwise from the hidden dim to the output. And that's it. Okay, now the thing to, yep, okay, it filled in. So I'll actually let it fill in because it's correct. So the thing to note is we're going to take our input, we're going to run it through this, and then for every time we run it, and we want to do that too. Okay, so every time we run it, we want to add our input back into the output. So this is where'd it go? Let me get back in this here. ResNet. That's what they're called. We want to do this plus piece. So we take the input, we add it, so that's the identity, right? Because you're keeping the same thing, and that just helps the model know that it's keeping some of the characteristics of its input, sort of. And that's about it. That's that. That will be our model. Let's go ahead and fix our syntax error. There we go. Well, sure. Depth, let's just go 1, and I'm actually gonna hidden dim out channels. I'm gonna say let's go. Before we had 5 and 2. Let's keep that the same, and we should now. 5 channels. Something's getting. Okay, anyhow, we're getting some errors here, so and it's on the first one, and it's because it says 64 expected input to have 5 channels, but got 3 because our data, 5. Oh, yep, you can't, that first one, you can't add it back in. You have to do the dimension first. That was my bad. Okay, cool. So yeah, let me talk about that for a second. So this first conv 2D, and I actually kind of like having that be a kernel size of 1 anyways too. Keeps it simpler. So we're doing a pointwise convolution on the part where we go from the input and dimension to the hidden dimension. So it's kind of like you don't let there be any spatial talk. It's just a pure projection into a higher dimension. And then here we do the spatial part. So all of the spatial stuff is internal to the model, and then again, output. It's just a pure regression on each pixel. Okay, cool. So this model works. We're good to go on that as well. We can create it. We can do that. It does exactly what we want. So let's go ahead and create a. Oh, I have a lag in my mouse. Create this. Okay. Down over here. Grab all of this. Okay. Boom. Okay. Data, model, done. Next up, training loop. So now we're going to try and put some of this together. We're going to need to actually do a couple, I guess what I would say is things that I don't love doing in my code, but it keeps the structure cleaner to have these notebooks and source. So if I want to actually import the source, the actual files or the data structures that we've implemented in those files in source, we're going to need to get this going. Okay, so first we'll import sys, and then we'll do yeah, so it's just a little bit easier for code to do that. So what we're doing, dot dot, again for reference, says put, let's close up venv, put, so we're at our base level. So I'm saying put everything that's in this area into my path. And that lets me do from src import model. Let's run that. So now we've imported from source model. We can even do one better and do something that is much easier. So now I can make a ResNet by saying, yeah, see, it doesn't know what's going on. 5 to 64 2. Yeah, see, the code has no idea what's going on. But see, we can create our ResNet, which now, as you can see, has our first convolution, then it's got our double conv blocks, and then it's got our output convolution. So we've basically imported this code here that we wrote over here and transferred to here. So all we've done is make this modular and nice. So that's what we want. And then from source.data, import GFS dataset. Nice. Good. So we can start building this out. So we will need to create some configuration-y things. So some stuff like what should these values be? What should these values be? So we should probably try to separate those all out and talk about exactly what we need, and then we can actually run the training step more or less. So let's try and do this cleanly and separately, but you know, it's always a little bit of a mix.